Okay, welcome in. This video, we're going to talk about optimization in R. Optimization is obviously a super complicated, super useful, but super complicated topic. So we're not going to do all of optimization being possible in a short video, but we're going to give you the basics of working with optimization in R, specifically through the kind of most central, I think, R optimization function, which is optim. But before we get to optim, we need something to optimize. I'm going to start by defining a function called, I've actually already defined it, so I'm going to remove it when I was prepping for this video. We're going to call this function, remember I like to name functions capital FUN at the beginning, so we remember it's a function. We're going to call it poly, short for polynomial, and it's just going to be a function of X. We're just going to talk about single variable optimization in this video. Maybe another video we'll talk about more complicated optimization. And we'll do a simple example. We'll do negative x plus 4 squared is going to be our function. So just a simple polynomial term. And, if we want to see like a plot of what this function looks like, we can define an x value and a y value. So x is just going to run from negative 10 to 10. That's what this colon does. We say x from negative 10 to 10. And y is we're just going to apply that function fun poly over x. R is nice, it's vectorized. We can just plug in a vector x and fun poly will apply over the vector, and we get kind of our values of y here. And if we want to see what this looks like, we can just plot x and y, and I have to make my screen bigger. Okay, even bigger apparently. Plot x, y, there we go. Very squished. Okay, so here's our function of x of fun poly, x on the x-axis and the y value on the y-axis. And you can see, as you probably know, when we type this, if you're familiar, not familiar, but if you remember your algebra, this function is going to be maximized at x equals -4, because when x, don't want to do that. When x is -4, this term is going to be 0. When x is anything other than -4, we are going to take the square and then make it negative. And I should this is a bit confusing. This is kind of the order of operations here. We're taking the square of something and then we're making it negative, which is why you see all these negative values here. So anything that's not 0 out of x plus 4 is going to have a negative value. So this is maximized at x equals -4. And I'll just plot that again for just confirming. So there we go, maximize at -4. Now that we know it's maximized at -4, let's actually do that with our optim function. Of course, when you're actually optimizing things, you don't know what the optimization will be. This is just an example so that we know the optimization, we know the maximum going in, so we can check our work and make sure that optim does the right thing. So for optim, the first argument usually is par. I don't really know what it stands for, but it's the value we want to start the optimization at. So you can think of optim as like, it takes in the function, it starts at a certain value, and it looks for all these different values over the function, all these different x values, and it tries to figure out the value that maximizes or minimizes the function. So we're going to start at 0. I think that's a reasonable place to start. That's probably where you start in most functions. I think the default in optim may be 0. So we're going to start it at 0, and it's going to look around 0 for the maximum or minimum. And in this case, we want to say the function that we're maximizing or minimizing. In that case, in here, it's just going to be fun poly. So we're starting at 0, and we're starting this argument x at 0, and then optim is going to look around in fun poly and optimize it. So I'm going to run it. I'm getting a bunch of weird messages just because of the plots, but I run it and I get these results. So this is a little bit weird. The results are a little bit strange to read. That's what we're going to talk about in this video. This $par output, this is the actual value of x that the optim found. So our optimized value is 1.8 times 10 to the 74th. So that seems weird, a really, really big number. And then value is the actual value of our function. When we plug in this x value into our function, we get this value, which is -3.2, -3.3 times 10 to the 148. So that's really weird. We got a really big value, really big x value, and a really really negative output of the function. We got that it did converge, but this looks pretty strange because we know that this function should be optimized at, should be maximized at -4, and we got this crazy huge value. And the reason why is because Optim by default minimizes functions. And I think it's because it's easier to do. I'm not positive why it does that, but by default, it will minimize a function. So in this case, it makes sense that we have a huge x value because the bigger that x is, the more negative that the output of this function will be. So it makes sense that we got this value. Ours basically, Optim is just like, here's a huge value of x. We're going to get a really negative, super negative value for the function, and we minimize the function. Hooray. We went all the way down and minimize the function. That's obviously not what we want. So there are two ways to adjust this. One, we can multiply our output by -1. So we kind of flip it, it's currently like this. We could flip it like our parabola looks like this. We could flip it so it looks like this. The way to do that is just to multiply the output by -1. Here I could have just taken away the negative, but I think this is a little bit clearer. And if I define fun poly again, and then I optimize, in this case, I get a lot closer to the answer. I get, we didn't get quite to the answer, and we'll talk about that in a second, but we got very close to -4 for x, and it got close to, in this case, minimizing, because this is, we're minimizing the output of the function. So that's one way to do it, is just to flip the sign of the function. The way I like to do it is not to change the function at all, because that can get confusing. And we just add in an argument into Optim, control equals list, fn scale equals -1. And this is like, I don't really know like that why it's a list, or I think it's because this argument control can take in a list of different arguments, and one of them is fn scale, and this is basically just saying how to scale the function. We want to scale by -1. So essentially this -1 is doing the same thing as multiplying this output by -1. We're just flipping the function upside down, and so this will take a maximum instead of a minimum, and here you can see we get the -3.8 and the -0.04 for our out. If we plug in -0.38 to our function fun poly, we're going to get -0.04, which is the value here. We didn't get a convergence though, which is sad. And you probably can tell, like, this is a pretty easy function to optimize. You can optimize it as a human. When you turn to Optim, you're going to be optimizing much more complicated functions. So why is this wrong? Why didn't we get the right value? And you've probably been seeing this warning message here. And the warning is telling us that one-dimensional optimization by Nelder-Mead is unreliable. Use Brent or optimize directly. So for some reason, the default method, there's a bunch of different methods in Optim. There's an argument that it specifies what method you want to use. And there's a bunch of different approaches that you can use to optimize things. The default is this Nelder-Mead, but it's not good for one-dimensional optimization, which is probably going to be most of your optimization uses. So you can either use this other function optimize. What I like to do is just to use this Brent method. So we're going to define our method as Brent. And when we define our method as Brent, we also have to define the space that we're going to look at. We have to define where Optim is going to look for the solution. So we define a lower bound as, let's say, -100 and an upper bound as 100. In this case, this is a pretty wide range. And basically we're telling Optim to look in this range for the solution of for the maximization of this function. And if we run this, voila, we get the correct answer. The function is maximized at x equals -4. This is the value of the function at that point. It's basically 0, -1 times 10 to the -29. So 29 zeros, 28 zeros, and a 1. It's just like it didn't. This is just silly, like coding asymptote. Why this isn't 0 and why this converges to 0. But we got a very clean answer for our output of our function. And again, just to check, we can check fun poly -4. That's going to spit out 0. And it's nice because we set our lower and upper bound to be pretty wide. We can like kind of stress test this. Let's say we start at the par equals 50. So we start the optimization looking at the value 50. It's still going to find -4. Even if we start at 50, it's still going to find the right answer. And let's really blow things up. Let's say the lower bound is 10,000 and the upper bound is 10,000. And let's say we start at 6,743. And I actually haven't tried this, so we'll see if this works. And look, it's still fine. It actually, in this case, gets exactly a value of negative, or exactly an output of 0. But if we set the space from negative 10,000 to 10,000, we start at almost 7,000, it's still going to find the optimum, which is x equals -4. So pretty, and this is a simple one-dimensional case, but I think it's reassuring that it pretty quickly and pretty easily finds the maximum over such a complicated sample space, or a complicated space. So that's basically Optim. I think it's important to remember kind of just the setup. We're starting, par is the argument, right? The argument of the function that we start at. So in this case, we're starting at x equals 6743. Fn function is the function we want to optimize, obviously fun poly. This control thing tells us we want to maximize instead of minimize. Usually you want to maximize. If you want to minimize, just leave this function, just leave this out. Or you could just put 1 here. I think that would work as well, but you can just leave it out. If you're doing one-dimensional, you want to use Brent, and then you have to set the lower and upper bounds for the optimization to actually look over. You have to tell it where you want it to look. And usually you want to set this to be wide because you don't know where as a human, you don't know where the optimum is, or the maximum or minimum is. So that's it for optimization. Again, this can get much more complicated. Maybe we'll do another video on it, but optim is a pretty powerful function. And if you define your functions correctly and you're passing in the argument that you want to optimize, it can be very powerful and useful in all sorts of coding and math. So hopefully you've enjoyed this, and we will see you next time.